Hello and welcome to Lecture 23. Here we're going to discuss Section 7.4. All right, so this section is all about the forces of uniform circular motion. Okay, could this apply to non-uniform circular motion, which we've already been talking about, angular acceleration and so on? Yes, but the focus here is going to be on uniform circular motion because there's a lot to talk about just in a case where the velocity at some moment in time, at least, is constant. So a lot of the ideas we're going to see that we've seen before, and in a sense, there's just one simple premise for this whole lecture, and that's that we take centripetal acceleration, which we've also called radial acceleration, just v squared over r, and multiply it by m. Okay, that's all we're doing. We're taking something we already have seen and worked with, and its components relative to the radial axis and the tangential axis. So those ideas, and all we're doing is just tacking on inertia. Okay. In doing so, in considering forces, something's going to happen that we always do when we consider forces. We're going to have a lot of these mechanical system situations. When we did a lot of force problems to highlight Newton's second law, it was ramps and carts and and pulleys and ramps and pulleys together. So here it's going to be similarly pendulums, conical pendulums. It's going to be racetracks and cars going around racetracks. So there's going to be a couple of very tangible examples that are going to dominate the lecture, okay? And those can be a little tricky to work with because they may be because of that real life aspect, but also they maybe make sense, okay? But it's all going to be the same physics, just with an application to a couple of examples, okay? So without further ado, let's define two quick key terms: centripetal force and centrifugal force. So, okay. Centripetal force, really nothing new. It's just the force that creates circular motion. It's just m times centripetal acceleration, otherwise known as m times radial acceleration. That's all it is. It's m v squared over r. That is the centripetal force. We don't really ever call it the radial force, which is part of the kind of naming issue here between centripetal and radial. The reason we probably would never want to call the centripetal force the radial force is because more than likely you might be talking about the radial component of other forces like gravity. So to call something the radial force is confusing. We didn't have that issue so much with the centripetal acceleration. Okay? So it is what it is, but we have the centripetal force. Okay? The force that points in the direction of the radius, the radial direction. What can we say about it? Well, tension, friction, gravity, the normal force, and their components are all, or can potentially all be centripetal forces. Because the centripetal force isn't a force that just comes out of nowhere. There has to be a non-contact force, like gravity, or a contact force, a reaction according to Newton's third law, like tension, friction, or the normal force. You push on something, it pushes back. That pushback might achieve circular motion, okay? And I singled out gravity because gravity is a different type of force. It's a fundamental force. We'll cover that in our chapter on gravity, okay? But these others are all, reaction forces to something. Anyway, so that can spin you in a circle. All those centripetal forces, wherever they may come from, it always points towards the center of the circular path. That's the definition. When I mentioned the centripetal acceleration, I probably mentioned, but if I haven't, that word, the etymology of the word is center seeking. So centripetal means center seeking. So it's the center seeking force. Okay? All right. So now the centrifugal force. We haven't talked about this, and there's a reason, because it's not a real force. Just plain and simple. Okay? It is a fictitious or apparent force that objects in circular motion seem to experience. It is not a real force because it is not measured in an inertial reference frame. An inertial reference frame is a place you make measurements that isn't accelerating. You're either moving at constant velocity or you're at rest. That's an inertial reference frame. Okay? The apparent existence of the centrifugal force is just a consequence of Newton's first law, which is the law of inertia. Things want to continue into motion. So if you imagine going around a turn, say a turn that turns to the left, the car is turning towards the left. People inside the car want to continue straight. Okay? Now eventually the seats, the reaction forces with the seat belts are going to push them in the direction the car is going, but they want to go straight, so they seem to experience a force to the right. the opposite direction of the turn. That's why we actually have a name for it, because that centrifugal force is such a common experience. But it's not a real force. It's just a desire of matter to continue in the direction it's going, which is Newton's first law. All right? It's no different than the idea that if you slam on the brake, things that aren't, slam on the brakes of a car, things that aren't attached fly forward. There's no force throwing those forward to the front of the car. It's just that they have inertia and want to continue at the previous velocity of the car. Okay, so it's that idea, but it's the turning version of it. And that creates this fictitious force called the centrifugal force. Okay, not a real force. All right, okay. All right, so let's get into the formulas, not too much. Okay, here's just a picture of going around a circular path. This would be an example of non-uniform circular motion, despite the name of the lecture. But I included it here because at any moment, there is an instantaneous velocity, and we can treat that velocity as uniform circular motion. We can consider its centripetal force, or the centripetal force that's associated with that translational velocity. So at any point in a non-uniform circular motion path, so a path where alpha is not equal to 0, where there is angular acceleration, well, you can still look at little instances and do all the force considerations. Okay, so that's important. So it can apply to things like pendulums, which definitely are non-constant angular acceleration, and of course then non-constant translational acceleration, all right, which means that your magnitude of velocity is changing. Your velocity is changing. The direction is always changing in circular motion, but if your magnitude is changing, that's called non-uniform circular motion. But regardless, the thing here, the thing of notice, is we still have our tangential and radial axes. We're still going to kind of think about the motion relative to those axes. We still have a radius of our circular path, and the only difference is that, I'll zoom in a bit, is that instead of just considering, accelerations, right, with the radial acceleration and the tangential acceleration, the translational ones, well, now we just have forces. We have the radial force, which we call the centripetal force, okay, again the name, and then we have the tangential component of whatever force there may be, and then we have the net force, okay? So it's just all the same ideas of acceleration, but instead they're forces, okay? And our main focus is going to be on the centripetal force and how that interacts with other forces like gravity and so on, or how it's created by them, okay? So the centripetal force is just mass times the centripetal acceleration. So it is, by definition, m times v squared over r. That right there is the centripetal force, okay? Now, of course, v equals omega r, so with the substitution, we can see the centripetal force in terms of angular kinematic quantities is m omega squared r, where omega is the angular velocity. Okay, so let's label some things. Centripetal force also can be called the radial force. Okay, we have the mass, we have the centripetal acceleration. These are a bit, these need to be moved over. Sorry for that, small typo. All right, we have the velocity, right, squared. Okay, and then we have the radius of the circular path, r. Okay, and the omega is the angular velocity. Okay, then we have our next line of formulas. We just have the definition of a period, which is equal to 1 over the frequency. Okay, so this is just how long it takes to make a full revolution, and this is how many revolutions per second something is spinning. That's useful sometimes because that's given in a problem instead of the instantaneous velocity. But since that the magnitude of the velocity won't change in a situation where it's uniform, okay, which is most of the situations, then we can then relate the period and the circumference of the circular motion to find the velocity, right? Because velocity for uniform circular motion is just circumference over period, right? Okay, and then we can split up, like here we're just seeing, we can split up the total force acting on an object in circular motion, either at an instant in time or the constant magnitude in the case of uniform circular motion. But either way, it is the force vector is equal to the centripetal component times the radial direction, the unit vector in the radial direction, and the tangential component of the force times the unit vector in the tangential direction. Okay? Tangential, really think of it as parallel to velocity, and radial, pointing towards the center. Okay, let's get to those examples, right? Let's do some practice. Okay, so there's 3 types of problems we're going to look at here. Problems that involve uniform circular motion where all the force vectors are in the plane of the loop, so very much like 2D and really mostly 1D in terms of our force considerations, okay? So 2D in the sense that, it's a plane of a loop, but really forces are 1D. Moving on, type 2, fairly complex problems that involve uniform circular motion where force vectors can be tilted to the plane of the loop. So this is, really think of type 2, you're going to have to take components. There's going to be some angle, and you're going to be taking components of forces. Those are going to be banked turns for cars and conical pendulums, which is like a tetherball. Okay. Then type 3, fairly complex problems that involve conservation of energy in circular motion, where instantaneous motion can be treated, I've been saying this a couple times, can be treated as uniform circular motion for an instant in time, where all the force vectors are in the plane of the loop. Okay. So luckily, all our ones that have the extra step of energy conservation aren't going to have as many components. Now, to be fair, you might still have components within the plane of the loop, but you're not going to have components of your forces, relative to the radial direction. Okay, so maybe it's either way they can be a little bit complex, but important thing with type 3 is you got an extra step of energy conservation, usually relating potential energy to kinetic energy. Okay. So let's do our first rather simple problem, okay? So a person swings a ball on the end of a string in a circle above their head, okay? Now the ball has a given mass and the string has a certain length, okay? So it's the radius. The string is assumed to be massless and the ball experiences negligible air drag, okay, that's important. The person maintains a constant rate of rotation while swinging the ball, okay, so definitely uniform circular motion, and it makes 4 complete rotations a second, all right? So question A, what is the angular velocity of the ball? All right, so to do that, we're going to use this formula here, the circumference over period, all right? And we have all the values we need, so we can find out then that the translational velocity of the ball is 19.4 meters per second, okay? All right, so then to find the angular velocity, we would, I guess I only give you the translational velocity. Sorry for that. If we wanted to find the angular velocity, we would simply divide by r. So it would just be 19.4 divided by our 0.77. So it'd be something on the order of like 25 radians per second. Okay? All right. So carrying on. And since this is a planar type problem, all right, we are assuming the string is rigid. Okay? So it's definitely an unusual assumption. There should be a little bit of a tilt because of gravity, right? So in other words, instead of it being perfectly planar, it should be going down a little bit. Now, it definitely would significantly complicate the problem. So here we're ignoring it, okay? But we will do a problem like that in just a moment. So then the only force in the radial direction is a centripetal force, okay? And that's then by Newton's second law, that's equal to mass times acceleration, the acceleration being the centripetal acceleration. Okay, so it's this kind of idea that, because we're going to do this idea, we're going to use Newton's second law, and it's always all the forces that create the centripetal force and then equal to m times AC, in other words, m times v squared over r. So the centripetal force here is entirely created by the tension, okay? And it's not a component of the tension, it's just the tension itself because it's a planar type of rotational problem, okay? And so in other words, the tension is just equal to m times v squared over r, all right? So here we're just finding the tension, part B, which is just 657 newtons, okay? All right? So let's do a concept question. We've done a simple example, just to kind of show how we would set up a problem like this. Let's do a concept question and make sure we have some intuition of the ranking of things. So the figure shows bird's eye views of a particle moving in a horizontal circle, so kind of like the problem above, right? On a tabletop in this case, which would then be more truly horizontal because the normal force is preventing any angle. All are moving at the same speed, okay? So they're all v, okay? And we want to rank in order from largest to smallest the tensions, okay? All right, so it's like the problem above, but truly planar, okay? And more justifiably. So there's your answer. Easy enough, right? Now, let's explain why. So let's call number 1, let's call that just T1. And so based on this idea here, the net force argument, we have that the tension is then just equal to m times AC, or just m times v squared over r, okay? All right, so that's kind of, this is going to be the tension that we compare to. So if we consider T2, well, the m is the same, the v is the same, but the radius is doubled. That means that T2 is 1/2 of T1, okay? So that means that T2 is definitely smaller. And we're going to rank from largest to smallest, so we see T2 is the last one. So having a bigger radius means less tension, okay? So the bigger the radius, the smaller the tension, okay? All right, so then moving on here, we've doubled the mass, but kept the radius the same. So then T3 is going to be twice T1. It's bigger, right? So in other words, having a bigger mass means more tension. That makes sense, okay? And then 4, we double both things, but since they one's in the numerator, one's in the denominator, they effectively cancel out, the 2's do, and so then T4 has the same magnitude as T1. Okay? All right. So thus our ranking from largest to smallest. Okay? Okay. So the tighter circle is the largest tension. Okay, especially because it's a tight circle with big mass. All right. So let's look at our next one here. All right, example 2. So example 2 is definitely a non-uniform circular motion problem, although it's kind of a simple idea. So it's like just swinging something through the top of a loop. But we're only concerned with the forces at the top. And at that moment in time, velocity is constant. So a bucket of water is swung in a vertical circle, so the bucket travels upside down, but the water does not spill. Right? You could definitely imagine that happening. Maybe you've done it. All right. In this case, the string has a length of 1.6 meters. The bucket has a known mass of 2.4 kilograms, and the water inside weighs 4 kilograms. All right. So the speed of the bucket at the top is constant. So what is the minimum speed of that the bucket needs in order for traveling through the top, in order for the water to not spill out? Okay. So the idea is that you want the water to be momentarily weightless. So let's consider the forces acting on the water. There is potentially a normal force pushing from the bottom of the bucket, and there's definitely gravity. Okay, we're going to define positive y's in the radial direction. We could have just called it r, but I'm calling it y. So the net forces in the y direction are going to be gravity plus the normal force equals mass times the centripetal acceleration. So this is a really important idea to really think about what we're doing here, right? We're just taking F net equals ma. Well, a lot of situations, a 0, right? Because there's no acceleration in that direction. Or maybe a is g or something. But here, or maybe we're solving for a in the case of like a pendulum. But here, notice that a is always v squared over r, because what we're saying is at this moment in time, the acceleration is causing you to turn, and specifically turn as a perfect circle, not an ellipse, not a parabola. And when you're turning at a moment in time as a perfect circle, that's your acceleration. Okay, so that's the argument here. Sometimes it's easy to miss that, right? So, by the way, when we have this type of problem, what's going to happen is the normal force needs to be 0, okay? Because the normal force being 0 is the condition of going just fast enough that weightlessness is achieved, okay? But not too slow so that the water actually falls out. Because if you go too slow, then you have excess gravity in a sense. Your gravity isn't being completely supplied into your mass times centripetal acceleration. You want to have just enough gravity so it's all being used up for the turn. The acceleration of gravity is just perfectly sufficient to cause a circular turn. Okay? If you're going too slow, you have excess gravity and the water falls out. If you're going faster than you need to, the water definitely doesn't fall, but you would have a normal force, because then you have extra MAC, right? So gravity is, is smaller than enough for the turn. And so you need an extra force to maintain the turn. Where does the extra force go for this faster turn? The extra force comes from the normal force, okay? But in the case where it's just perfectly balanced, that minimum velocity for the water not to fall, normal force is 0, okay? And that's what we're show here. I go ahead and solve for V, just doing the algebra, right? Just isolating the V, but then cancel out that normal force as the final step, justifying the fact that it needs to be 0 for minimum velocity, all right? Then we just plug in the numbers, because once we cancel the normal force, the m's cancel, and we're just left with the square root of Lg, right? Really elegant result. And it ends up being that the minimum velocity to make it around with the water not spilling is 3.96 meters per second. Okay? All right, so let's zoom in our part B. So in part B, we're asked what is the tension in the string when this minimum speed is achieved. So what do you think it's going to be? If the water is momentarily weightless, if we're going through the loop just fast enough for it to make it through without spilling, wouldn't you expect the tension to be 0, right? Because the whole system is just like hovering there for a second before it then starts to go down on the downswing, okay? So we should expect the tension to be 0, and indeed we can show it is, okay? So if we consider the bucket now instead of the water, the forces acting on the bucket are the tension and gravity. So it's tension instead of the normal force. We're then going to plug in the total mass, because that's the inertia now, because the water is inside the bucket, so it has to be considered. All right, and then we also have the total mass on the left-hand side or the right-hand side of Newton's second law, the ma part of F net equals ma. Okay, and then we just plug in what we know. Well, we know that v for minimum velocity has the formula square root of Lg. The square root cancels with the square, and so then we just have Lg over L, so the L's cancel. All right. And so then we find that the normal force is just going to be m times g minus m times g, m total in both cases. Well, that means that it has to be 0. All right, so just by taking the algebraic form of the minimum velocity, we find that any other forces have to also be 0. Okay, on the other, if whatever other system we're looking at, because the bucket and the water are connected. Okay, all right, and then finally, in part C, what constant speed does the bucket need at the top of the swing in order for the normal force to not be 0 and in fact be 20 newtons? All right, well that's I said the normal force comes up when there's excess velocity, so we should expect the velocity bigger than 3.96. So in this case, it's going so fast there's got to be some more force to achieve the turn. Gravity's not enough. All right, so what we do then is we just set up the same net force equation, and then we just solve for the velocity. In this case, the normal force doesn't go to 0, it's a known value. We plug everything in, and we find that it is indeed faster than 3.96. It's 4.87 meters per second to achieve that particular magnitude normal force of 20 newtons. Okay? All right, for this particular mass, by the way. Okay, if we changed either, then the velocity would change. All right, so there you go. Okay, let's do some more examples. Okay, so another kind of simple one in a planar case. In this case, considering a car going over the top of a hill. So a stunt car is going over the top of a hill that has a circular curvature with a known radius, 102 meters. All right, what is the maximum speed they can go over the hill and not become airborne? So here's the picture. All right, so the maximum speed is reached when the normal force equals 0. All right, so here's kind of the same idea. We're having that moment of weightlessness, but here it's at the top of something. Okay, if they go any faster, then it won't be a moment of weightlessness. They'll actually become a projectile. Okay, and so we don't want that to happen. We want weightlessness without being airborne. Okay, so then in that case, the only force in the radial direction is gravity, and that's going to be equal to MAC, or in other words, m times v squared over r. And then we cancel out our m's and just solve for v, and it's just the square root of rg. Look, it has the same form. It's just that it's r instead of l because they're both the radius, just whatever is appropriate to the system. Before it was l for length, here it's just really r for radius. Okay, and then the number ends up being 31.6 meters per second. So it was totally independent of the mass of the car, which why it wasn't even given in the problem, and it was just dependent on the radius. The bigger the radius, the bigger the velocity that you can push it without becoming airborne. Okay, all right. So similar idea, right? Hopefully that makes sense. Okay, so let's expand on this a bit. So this first one, again, is planar. We're doing quite a few of them. The reason I went ahead and included it, not to be repetitive, but because it's going to be kind of a segue of car problems. It'll be one of 3 problems that involve a car going around a turn. Okay, we've done a car over a hill, but now we're going to do cars on turns that we can kind of see from a bird's eye view. Okay, because that's an important system. It's one I like to focus on because I think it's very concrete and we can play around with it and change variables and make it gradually more complicated. Okay, so this is the simplest case. We have an unbanked curve with a radius of 80 meters, and we want sufficient friction for the car to make the turn without slipping at a speed of 19.4 meters per second. Okay, so the car wants to maintain that speed, and we need enough friction to pull it off. Okay, unbanked means like flat. So if you think of a racetrack, the turn is banked, right? It's tilted inwards. All right, so this isn't that. This is unbanked. It's totally flat road. Or even if you think of like steep mountain roads, they're always banked on the switchbacks, on the tight turns. Here's the bird's eye view, right, of our turn. We're going to consider the forces in the radial direction and the y direction, and the y direction would be out of the page towards you, okay? Because we're looking down at it, so y would be up towards you. It's not drawn, but it'd be up towards you. So the radial direction is just the friction force, okay? And that's going to be equal to MAC. And then in the y direction, there's gravity pointing down into the page and the normal force pointing up, okay? And the two of those together, we can see, since they're equal to 0, because there is no acceleration in or out of the page, that we see then that the normal force is just equal to mg, okay? So it's really kind of that's a result that we can almost just take for granted for anything that's flat like this, but I wanted to show where it comes from just as a reminder in case you've forgotten. And that means that then when we substitute in for the definition of the friction force, and the friction force by definition is mu s Fn, well then Fn is just mg, all right? And quick note here, with all cars on banked turns, it's always the static friction. And you might say, wait, but cars are moving, why isn't it kinetic? Well, because the actual contact point of the tire is not moving. We'll talk about that more when we talk about the concept of rolling motion in the next chapter, But for now, just understand that there's no translation of the contact point of the tire for an ideal rolling tire. So it always has to be static friction. Okay. All right. So mu s mg equal to m v squared over r. So the m's cancel. So it's totally independent of the mass of the car. And then when we solve for that friction coefficient, it's just v squared over rg. Right. So we have kind of the direct relationship to particular variables: how fast you're going and how wide the turn is. Okay. And what planet you're on, g. So plug in the numbers that we were given: the velocity, the radius of the turn, gravitational acceleration, and we find that a fairly large static friction coefficient is necessary for the car to not slip, 0.48. So maybe they should have built this turn with banking, especially if they expect cars to go that fast around it. Okay, all right. So, right, because if it gets wet, it's going to have less friction than that. So now let's complicate it a bit. Let's consider a banked turn, but let's consider a banked turn without any friction. Okay, so the idea is that friction isn't needed. So this is a turn you could take on like an icy day. So that's also kind of a bit of a silly concept, or maybe it's just over engineering, right? They want people to make this turn more, with more than enough safety. So they want it to be able to be achieved with an assumption of no friction. Okay, so on a really wet day, if an oil spill, you can still make it. Okay, all right. So same view from the top, but we also have to consider a view from the side. Okay, the reason is because now we have our banking angle theta. And that means that there is potentially more forces at play that are going to create the centripetal force. In this case, without friction, it's fairly simple. I'll zoom in a bit more. The only force that's in the radial direction is the x component of the normal force. That's it. That's the only force we have to look at. Okay? So we have to find the magnitude of that force. So that's why we have a full free body diagram here. But ultimately, it's only this force in the radial direction. Okay? Now, the natural question, if you're paying attention or thinking about solving a lot of free body diagrams, is you might say to yourself, why do I not have a tilted coordinate system? You always have tilted coordinate systems when you have an object on a ramp. And this car's on a ramp, isn't it? We call it a bank, a banked turn, but it's still a ramp from the side. Well, the reason I don't have a tilted coordinate system is because the acceleration is entirely in the x direction, and I don't want to take components of my acceleration. You can still solve the problem, but you'd be giving yourself more algebraic trouble. So it's actually better in the case of centripetal motion to leave the centripetal acceleration vector, because there really is a subscript c there, along or parallel to some axis. In this case, I'm calling it the x-axis. And if that's the case, then my other axis has to be straight up. It's the y-axis, has to be vertical, which means I'm forced to take components of my normal force, okay? Which we don't normally do, okay? Now, on the other hand, the bright side is I don't have to take components of my gravitational force. But we're not used to taking components of the normal force. So make sure that you're not kind of overthinking it and thinking like, well, how do I take components of the normal force? Just like you would any force, okay? So let's look at what it looks like. The sum of forces, the net force equations. So the net force in x is simply the x component of the normal force. That's equal to m times centripetal acceleration. In the y direction, it's just the y component of the normal force minus gravity, equal to 0 because there's no acceleration in the y direction. Okay, that's why I chose my coordinate axis. So, okay, so let's plug in the full forms of them. So f and x is just fn sine theta, y sine theta. We'll look at the triangle right here. Okay, f and y is fn cosine theta. All right, so that's really all I've done here. Okay, and then I'm going to go ahead and solve for fn. So fn has a value of mg divided by cosine theta. Okay, and then I'm going to substitute that in to the f net x equation, because I used f net y to solve for fn. So when I substitute it in, right there, I have a term which is just mg sine theta over cosine theta. The sine theta because I've included this. Okay, so this is equal to this, I should say. Okay. All right, and then that's going to be equal to mass times centripetal acceleration. Here I write centripetal acceleration as v squared over r. Okay, and then we're just going to go ahead and note that sine theta over cosine theta is just tangent. And then I'm, after all, solving for theta. So all I need to do is, rewrite this as tangent theta, and then isolate the theta inside of the tangent, which means taking tangent inverse of v squared over r plus cross divide by g. So v squared over rg, all inside the inverse tangent. Okay? Now that's kind of cool because look, v squared over rg, that was exactly the ratio that showed up for the unbanked turn for friction. Isn't that neat? And here it was dimensionless and it was giving us the friction coefficient. Here v squared over rg is still dimensionless, but it's inside a trig function and it's going to give us the angle. So cool, okay? And so then we'll go ahead and plug in all our numbers and we find out that our banking angle is 25.6. So that's actually a really steep turn if you think about it. I mean, that's like racetrack steep. You actually wouldn't really see that anywhere outside of a racetrack on a normal road. But of course, this was a over-ambitious ask, wasn't it? To have a turn that was, rather tight at 80 meters that was banked so much that you could make it without any friction at all. That's why it's such a big number, such a steep angle, okay? All right, so we'll get back to cars going around turns in just a minute, but let's look at a different type of kind of 2D system, non-planar system, which is often called the conical pendulum, or I like to think of it as a playground tetherball, right? Think of like a, like elementary school playground tetherball. With this, it's just tetherballs going around, okay? But this is the tetherball going around where it's not wrapping around the pole, so it's just continuing in a nice cone-like motion, okay? So we know the mass here at the end of our pendulum, right? Just a mass attached to the end of a string. All right, and we know the length of that string or rope, and we know that it's spun at a rate of 30 RPM, and the question is, what's that angle? All right, so that's it. Just knowing the mass and the length and the rate, because this is constant uniform circular motion, we can actually find theta. Well, how would we do that? Well, it definitely doesn't involve forces, okay? So we're going to look at the forces in the x and y direction, okay? So it's kind of like a banked turn, right? But just a different version of it. And okay, so then we have the tension force, right? So now tension force has replaced the term normal force, same idea, different name because different physical process, right? And, just slightly different really. So the tension force, right? And sine of theta, well, why is that? Well, because you think about it, the x component is going to be this side here, right? That's the x component. And think of this right triangle. Well, that side is definitely the opposite side relative to theta, thus sine of theta, all right? So the x component of tension is just ft sine theta. It's going to be equal to m times v squared over r. That's what this is. This is v squared over r. But for some reason I wrote r as L sine theta. Why is that? Well, because we know L, but L is not r. L is the hypotenuse. R is this, okay? That is r. And r, based on this physical distance triangle, is just L sine theta, right? In the same way that Ft sine theta is the x component of the tension force, okay? So hopefully that makes sense. In the y direction, well, we've got Ft cosine theta, the other component of the tension force, minus gravity. And there's no acceleration in the y direction, okay? So we also want to relate our RPMs that we were given to velocity. So we know that velocity is 2 pi radius times frequency, so circumference times frequency, in the same way that velocity is circumference divided by period. It's also circumference times frequency, okay? And so then I'm just going to plug in that, that we got our 2 pi, replace r with L sine theta, like we already did, leave in our f there, okay? All right, so we'll come back to that. We're going to substitute that back in. But now let's look at our tension force, okay? So I know from my sum of forces in y that my tension force has the form of mg over cosine theta. Does that look familiar? Well, yeah, because that was the same form that the normal force took for the banked turn. See, because the tetherball is like a banked turn. Okay, all right, but we are solving for a different thing here. So mg over cosine theta, okay, all right, and then we're going to go ahead and substitute that in to our sum of forces in x, okay? So when I do that, notice what happens, okay? So I plug in my mg over here. So my ft becomes mg over cosine theta, which is right there. My sine theta gets multiplied, okay? On the right-hand side, I replace v with this whole expression. So I have 2 pi f squared times L squared sine theta squared, okay? So this is just the 2 pi f squared, all right? The L squared you can see right there. And then the sine theta squared is this, okay? Well, that's all divided by L sine theta, so a lot of things start canceling. What? Well, on the right-hand side, we have a sine theta cancel, and we have another sine theta cancel across the equality. Meanwhile, in this expression, we have an L in the numerator cancels with, or L squared in the numerator, one of which cancels with the only L in the denominator. The 2 pi f squared is entirely left. just like the g over cosine theta is left. Okay? All right, so what it looks like then is we have, when we cross multiply and isolate our cosine theta, we find that it's just g divided by 4 pi squared frequency squared times length. Okay? All right, and then I just want to isolate the theta. So then I'll just take cosine inverse of all the things that didn't cancel. All right, so then I just have my gravity, 4 pi squared. I convert my frequency over to hertz, which is revolutions per second, because I was given revolutions per minute. So it's that 30 divided by 60, right? Because if there's 30 per second, then there's if there's 30 revolutions per minute, then there's 1/2 of a revolution per second. That's why it's just 1/2. In other words, it takes 2 seconds to make a full revolution. All right, got to remember to square it, multiply it by the length, and there we have it, 63 degrees. Okay, all right, so maybe involved a bit more algebra, a bit more things to think about, but still very, very similar idea to the bank turn and finding the banking angle. Okay, but here we're finding the vertical angle, 63 degrees. Okay, all right, so now let's do one where we combine friction and banking. Okay, so a racetrack driver enters a bank turn with a 150 meter radius, so a little bit less tight turn than the 81 we saw twice, where the banking angle is 18.2 degrees. So we know the banking angle, okay? And the coefficient of static friction is 0.15. Okay, so fairly steep banking angle, fairly slick road. And the question is, what is the maximum speed that the driver can maintain in the turn and not slip up the banked track? So in other words, not start to lose control and go out of the turn, okay? Which means they'd slip up the embankment, okay? All right, so let's look at the free body diagram. All right, here it is. I'm not bothering to show the above view because I just want to focus on the thing we really care about, which is the side view. Now, yes, there's more going on. Why is there more going on? Well, the normal force we've already seen. This is exactly like the previous problem. The bank turn one at least. Okay, example 5. Okay, but here notice what's different. We also have the friction force. Okay, we have the same untilted coordinate axis because we don't want to take components of the acceleration, the centripetal acceleration, and we still have gravity. Okay. All right, so what are we going to do then? Well, we're going to take note that there's actually going to be 2 components that are going to create the centripetal force. The centripetal force is going to be the sum of Fnx and Ffx. Okay, so let's see what that looks like. All right, so I color-coded a couple equations because you're going to see them each once below in the algebra. So for quick reference, the F net x equation is orange and the F net y equation is green. What is F net x? Well, it's Fnx, so the x component of the normal force, plus the x component of the friction force equal to mass times centripetal acceleration. In the y direction, it's just the vertical or y component of the normal force minus the y component of the friction force minus gravity equals z, equals 0. All right, a z word, but equals 0. Okay? So there's a lot going on in the y direction. That's always kind of the first thing that maybe catches your eye, right? And that's because some of the friction is actually pointing down, okay? It has to be, because the friction is preventing the car from sliding up the embankment, which it will do if it goes too fast. So friction has to point down the turn, okay? The other version of this, by the way, is a car going around a steeply banked turn like a racetrack, but it's like let's say it's a snowy day or an icy day, the track is icy, and then there's actually a danger of the car going so slow that it actually starts to slip down the embankment. There's very specific circumstances for that to happen, right? But it could happen. In that case, the friction would have to point up. Okay, but that's a different problem. I bring it up because sometimes I ask a version of that problem. But here, we're worried about the car losing control and going up the bank turn. Okay, all right, so let's expand our forces. Okay, so I'm just going to rewrite the forces in the y direction with all the appropriate angles shown. All right, so the y component of the normal force is Fn cosine theta. The friction is defined as mu s Fn. All right, so that's just the definition of friction force. And then we're taking a component of the friction force, the y component, which is going to be the sine component. Okay, so you can see why. And that's always something that maybe, it's like, wait, why is one cosine and one sine? Well, look at the triangles. Just look at the right triangles. Okay, and then gravity is entirely in the y direction and it's negative. Okay, then we're going to solve for the normal force from this expression, from this the forces in the y direction. When we do that, just isolating the normal force, which shows up in 2 terms. And by adding mg to both sides, we just get mg divided by cosine theta minus mu s sine theta. Okay, so there we go. That's our expression for the normal force. All right, and we're then going to plug that in to this expression here. That way we can solve for v, because we're trying to solve for v, right? But we can't solve it as written because there's a bunch of unknowns here, right? Okay, we don't know the normal force. We don't know the friction force. We know the friction coefficient, but we don't know the friction force. Okay, so let's do that. So we substitute into the net forces in x. All right, so that's our orange equation. So what does that look like? Well, the first thing I'm going to do is I'm going to rewrite the forces in x by noting that this is Fn, so that's Fn sine theta, look at the triangle, plus mu s Fn, and the x1 would be cosine theta, okay? That's the whole left-hand side. So if I factor out the Fn, then it just looks like this. So I haven't actually substituted it in yet, I've just factored out the Fn from those two terms, okay? And that's equal to mass times centripetal acceleration. Then I'm going to do the substitution. I'm going to replace Fn with what we know it is from the sum of forces in the y direction. That's just this, see? Okay? And then, since we factored out the sine theta plus mu s cosine theta, they're still there, okay? Then we look at this whole expression, okay? And we cancel out the m from both sides, and then we just solve for v. And we're done, okay? We know the angle, and we know mu sub s, and we certainly know the radius of the turn in gravity. We have isolated v and solved for it, all right? And it actually has, although it looks like a lot going on, we can see there's a lot of symmetry here, right? It's rg, so radius times gravity, then times the sine theta plus mu s cosine theta divided by cosine theta minus mu s sine theta. So this kind of is the key. The key in a way that the coefficient of friction and the angle all interact together to tell you how fast you can go. Because you can think about what would happen is you vary one or both of those values. So in this case, the values we're given were 18.2 and 0.15, so we just go ahead and plug them in, and we find out that the max safe speed without losing control is 27.2 meters per second. All right, so there you have it. You know, fairly complicated free body diagram with this key idea that there is a form of acceleration, specifically a velocity-dependent acceleration. Okay, all right. Last two that involve energy. All right, so a pendulum is a great system to have conservation of energy combined with forces, okay, in this case. All right, so this is like a problem you've seen before with acceleration considered, but now there's forces instead. So, okay, so a pendulum with a string length, all right, is released from a height of 45.7. It has a bob with a known mass, and at the moment shown, the pendulum is a height of 13 centimeters. What is the angular velocity of the pendulum? And, the original version didn't say and, that's why you can see our place of handwriting. So pendulum and translational velocity of the bob. All right, so let's do that first. Okay, so we're going to consider a conservation of energy from state 1 to state 2, or point 1 to point 2. All right, so 1 to 2. At point 1, we have mg h naught, because that's where it's released from rest. So that's its initial point where it's all potential energy. And then by the time we get to point 2, we have kinetic energy and remaining height, a remaining height of 13 centimeters. All right. Okay, so yeah, all right. And then we're going to go ahead and solve, okay, for the velocity at that point. Okay, oh yeah, there's h naught, 45.7. Okay, and so then we can just plug in our 45.7 for h naught, our 13 for the final height, okay, but convert them to meters, obviously. So there we have them. And then we find that the velocity then at this point, at point 2, is 2.53 meters per second. That's how fast it's going, since some of the potential energy has been converted to kinetic energy. Not all of it, because it's not at its lowest point yet. It's still 13 centimeters above its lowest point, right? Because it has yet to swing all the way down. Okay? So notice we didn't need the angle because we were given the heights. And the heights is all we needed for finding the change in energy, the conservation of energy. If we were given the angle, we would have had to actually do some work. Okay? So now on to part B. What is the tension in the string? Okay? Oh, and by the way, I also asked for the angular velocity. So the angular velocity is just V over L. Okay, and this time I remember to do it. And so this is 3 radians per second. Okay? So then part B, and then use Newton's second law to find the tension force. Okay, as we've been doing, we're just going to consider the forces in the radial direction. So it's the tension force, okay, minus the radial component of the gravitational force. That's the net force in the radial direction. And that's equal to mass times centripetal acceleration, okay? All right. Well, here's the thing. we're going to need the angle after all. Why is that? Well, because we have a component of the gravitational force, right? If we're going to take a component of the gravitational force, we need to take cosine of theta. But we don't know theta, we just know the height of 13 centimeters, and we know the length of 84.3 centimeters. So we have to set up this familiar right triangle. I say familiar because I've done this in previous examples in previous lectures, right? Where this side of the triangle is h minus, or L minus h. Let me redraw this. So this is L minus h on this side. This is L, okay? And then we can just use that to find the angle, 32.2 degrees, okay? So here's the form of solving for the tension force. So it's mg cosine theta, because I just added to both sides of the equation, plus m times v squared over L. Factor out the m, 3.6. Plug in all our known values. Zoom in down on that. Okay. Plug them all in. And then we get our answer, 57.2 newtons. Okay. Looks good. All right. What angle does the net force on the bob make with the radial direction? Okay. So we just consider the net forces in both directions, the radial and tangential. The only force in the radial direction is a component of the gravitational force, the tangential component. Okay. All right. And here I'm just writing out their form. Okay, expanding them out. So then phi is just going to be tangent inverse of everything in the tangential direction, because you can see here, this is the angle phi. So it's just going to be the tangential side, the opposite side over the adjacent side. All right, well, the tangential side is just g sine theta. Everything in the radial side is going to be this right here. So it's tension, okay, minus fg cosine theta. Well, we already know what tension is, right? It's this, okay? So then I just cancel out the m from everything. That's why it doesn't show up here, okay? And then, so it's just the g cosine theta plus v squared over L, and then minus that component of gravity, but that's also g cosine theta, so it cancels out. Oh, that's interesting. So then when we write it, we get this. This is actually exactly what we would have got if we didn't even consider forces, if we just considered the accelerations. But that makes sense, because this answer should be independent of the mass, okay? All right, so then it ends up being tangent inverse of g sine theta over v squared over L. Plug in our numbers, and we get 34.5 degrees. Pretty large angle, because we're not that far to the bottom yet. We still have a pretty big angle, 32.2 degrees, with the vertical. So there's still a lot of acceleration yet to do, okay? So that means that the tangential acceleration is still busy, and the radial acceleration has not dominated the circular system yet, okay? Our circular motion. All right, last one here. This is another really kind of important type of problem. It's the loop-the-loop. I tend to do a lot of loop-the-loops, but in your book, we introduced energy before we introduced circular motion. So I held off on doing loop-the-loops in the energy examples, but here where it's totally fair game. So let's talk about the loop-the-loop. Neat system, okay? The idea is that this is a totally frictionless ideal system. We're going to release the box from some height. It's going to slide down, and it's going to have enough speed that it's going to slide all the way around and not fall off. But it has just enough speed to not fall off, so the normal force is 0 at the top. It's the whole idea that gravity is being used up for the turn, so there's not any excess force necessary because the turn is just slow enough for gravity to be sufficient for the box to go around, okay? But also for gravity to not be insufficient, so the box doesn't fall off at the top. It slides nicely, perfectly around, okay? So we're going to start with energy conservation between points 1 and 2. E1 equals E2. E1 is entirely gravitational potential because it was released from rest. By the time it gets to 2, it's got both forms of energy. It's got kinetic energy and it's got potential because it's 2r off of 0, because the 0 points down here, y equals 0, okay? All right, and 2r is less than h. This is somewhat drawn to scale. All right, and we consider that F net in the radial direction at the top of the loop for minimum velocity has a normal force of 0, just like the bucket of water. All right, so then the net forces in the radial direction are just going to be gravity equals mass times centripetal acceleration, which means that V is really simple. It's just the square root of RG. So then we can substitute that V back into our energy equation. All right, so then energy becomes GH, because the m's already canceled. So then it just becomes GH equals 1/2 times V, which we've replaced with the square root of RG, but we're squaring it, so the square root cancels, plus 2GR. This expression here, I put the 2 in front. The g's now are in all the terms, a g and a g and a g, because remember the square root's gone. So we cancel out that, and then we just find that h is equal to 1/2 r plus 2r, or 5/2 r, or 5/2 times 0.984 meters, or in this case, 2.46 meters. But here's the elegant part. It's 5/2 r. That's pretty cool for this nice ideal frictionless system. As long as you start at a height that is 2.5 times the radius, you'll make it through the loop. but it better be frictionless, okay? All right, so that's it for this chapter about centripetal forces. All right, I hope it's been interesting. I hope it's been a lot of helpful examples to kind of see what it looks like to solve these types of problems. Thank you so much for watching.